Good morning, good afternoon, good evening. I'm Shravan Pagrut, a simulation consultant at SimWell, and I have my background in mechanical engineering, and I've been working with SimWell for the past 3 years. And with me today is Stephen Downing, an operations engineer at BlueScope Steel. Stephen has over 20 years of experience working with metallurgical processes and operations engineering. Today, we will be presenting the piece of work we did with BlueScope Steel, the largest steel manufacturer in Australia at their largest site in Port Kembla. We worked with BlueScope to model the impact of new additions they were making to the site. Before diving in, I would like to give you a brief summary of what this webinar would be like. Stephen, if we can move to the next slide. Yeah. So we'll first start with the problem statement and a brief summary of the high-level process of slab yard that will be given by Stephen, as well as the challenges that were faced in the process, and why BlueScope chose simulation-based approach, and why specifically AnyLogic was used for the task. And then we will delve into the modeling bits, and finally the methods that we used for confirming that the model was an accurate representation of the real-life process and the results and benefits it provided BlueScope with. Any questions that you have, you can write in the Q&A section. Now I'll hand over the podium to Stephen to delve deeper into what BlueScope does as well as the process. Thank you, Stephen.
Hello, everyone. Welcome today. Thanks for that introduction, Shravan. I'm here in our Port Kembla site, which is in a suburb of Wollongong in the Illawarra region of Australia. I'd like to just briefly acknowledge that Port Kembla sits on the Dharawal country, and we acknowledge the traditional custodians of these lands, the Wadi people, and would like to pay respects to elders past, present, and emerging. So BlueScope, formerly known as formerly a BHP site, has been operating in Port Kembla now for over 98 years. Our 100th anniversary is coming up in 2027. On this site, we are a traditional integrated steelworks. The area of this site that we focusing on is the plate mill, or the interaction between the plate mill and where our slabs are supplied from in the slab yard. So a traditional integrated steelworks, for those who aren't familiar, involves the processing of iron ore and coal through into a blast furnace, which produces the molten iron. This iron goes through another processing step to convert it into steel, which then is cast into slab. These slabs are then all funneled into a centrally located warehouse, from which they are then delivered to one of either on our site, the hot strip mill, or our plate mill, which is then rolled into our various products and then dispatched to either internally or externally to customers. So today we'll be focusing on the slab yard operations, specifically relating to feeding the plate mill as opposed to the hot strip mill. So as you can see here, we actually engaged in a major project at the moment. We've had a very exciting opportunity. The plate mill on this site is now over 60 years old. And so many manufacturers, people from the industry will understand using older equipment. We have done our very best over the decades to keep up with technology. But one of the areas that has always been, that is quite difficult, very capital intensive, is our reheat furnace. So we've had an opportunity now, the business with growth in infrastructure and renewables, to do some major $300 million investment into our plate mill to introduce a new reheat furnace. Now, this reheat furnace will be a walking beam furnace, give many technological advantages, but the challenge that we identified throughout our process of establishing this project is that our furnace is going to have to be bigger than the two existing ones. You see this purple structure here is one, and then the green structure next to it is number two of our two existing furnaces. For us to get the advantages, the efficiencies, we would need a much longer furnace, which is represented here with this red structure. And that will then impact the material flow of how these slabs you see here on the right are provided to the reheat furnace. So these changes represent quite a lot of unknowns at the start of our project, and there was significant concerns that the advantages of our projects was to deliver significant improvements in quality, significant improvements in efficiency, in environmental improvements with reduced carbon per ton of steel usage, but also significantly increase overall throughput, that the supply of these slabs from the slab yard area by these cranes may not be able to effectively keep up under all scenarios. So these are the things that we needed to assess. So as part of that process, as we started this, we had a significant contingency fund set up of multiple millions of dollars, which we had a number of solutions put forward from different areas of the business that we should consider, most of which were in excess of what we could set aside as our contingency for this project, some of which many times that. And so we had quite a significant risk to our project, to delivering on the future of steelmaking in the Illawarra. We feel it's intrinsically linked to maintaining a strong plate mill. And so we really had an urge to solve this issue. And as we looked into it, the complexities of it, we realized that a simulated approach to see the whole chain of movements, of bottlenecks and technical issues was what we needed to actually give us the answers and confidence to put this issue to bed and proceed with the project. So the areas of the slab yard consists of a number of activities. It starts with what we call rakes. Rakes are a string of rail wagons that bring the slabs from the slab caster. They come into the central upper, or what we call the upper yard in this case, and they all get unloaded in this area and they get stored. And as they are required for the downstream process, in the order that they are required, they will be sent across a transfer car down to the lower yard, where they are moved to a cutting compound. So we actually cast much larger slabs than what we charge into our plate mill furnaces. So their slabs need to be subdivided or slab cut, which are then stacked out in that area, removed from that area to a secondary area, which will then have to be assembled into quite a complex sequence. One of the requirements of rolling plate is a very complex scheduling process. So the slabs must be ordered in that before then being, when placed in order, put in front of our reheat furnace for the second crane in that area to charge them onto the feeding tables, where they then put inside the furnace. We have to make sure as part of this process that they receive the correct heating dynamics, correct time inside the furnace, before they're then discharged and rolled. And this last step is one of the most critical, because it actually defines the demand on the whole system, is the speed at which, and every individual slab has its own individual timing and requirements. And our goal here is always to maximize our productivity. So we need that reflected as well within the model. So to summarize, the scope of the model is from the arrival of slab from our slab caster all the way through all the various process steps to the heating and actual production of a slab into plate. It's all simulated within the one model. A critical step on that is how the cranes operate. They are, I guess, the heart of this model, and making sure that those are representative of real operating conditions specifically the way our cranes shadow. So our cranes have been manual cranes in the past. We've always had actually quite a lot of data collection from those cranes, but we've since in recent times moved to fully automated robotic cranes. So we have quite a defined methodology for how those cranes operate, and also quite a lot of data on how they perform. And so getting that representative was key for us. The existing furnace, of course, to know we have a good starting point, to have a confidence that we have the existing furnace modeled correctly in the existing process, representative for the outputs compared to what we see before we're moving on to then obviously the new furnace and how that would change the whole dynamics of the system, particularly the impact of the real estate being consumed by the new furnace. The entire model, obviously, as I said, configured to do these various scenarios and to produce a lot of reports, a lot of statistics, so we can compare each individual asset component compared to real life results to what we simulated to build our confidence in what we were seeing. That also, includes inventory. One of the area is essentially a large warehouse, and you could simplify it by calling it that, knowing that our inventory levels in different areas at different times that we don't exceed our maximums was also another critical point that we needed to identify. The challenges, many challenges throughout this process. It was fantastic working with SimWell on this to work through them. The increased productivity, ability of this to actually pull the slabs through at a faster rate than the existing furnaces. The modeling, obviously, of the crane to be representative of reality and how it was delivered at each step of the project, particularly to the furnace. And the fact that furnaces behave, the new furnace technology behaves quite differently in many regards. The priority-based tasks of the crane and how those cranes can be flexible. So though our cranes are automated, they have people in a control room who task their jobs, and they will identify competing priorities at times to change the tasking of the crane to make it the most efficient and as deliver to the mill as effectively as possible. The transfer car between yards, so that's actually essentially a finite resource and can become locked up if we're trying to do two actions at the same time, making sure that had its correct priorities. And that's also is key to managing our inventory levels in different areas. The modeling of the slab cutting process, which was in itself a process within a process, sort of a simulation within a simulation, as it were. And throughout this, we needed to represent our delays, and these different assets had their own delay scheduling as well. So our simulation, as I said, we identified pretty early that this would need to be simulated because given the, particularly if you consider the way slabs are scheduled to be provided into the yard versus the way the slabs are scheduled to be rolled. These are two very sort of disparate type scheduling approaches that don't have a very clear connection between the two. So no amount of spreadsheeting was going to be able to give us the answers, no amount of artificial developing of schedules. So we took the approach of building the simulation and using over 2 months worth of real live data of supply of slab, live data of crane movements, live data of cutting process, live data of the furnace and rolling process, to then build this simulation as the inputs to the simulation, to then compare back to what those outputs of that 2-month period was. Yeah, so lots of complex scheduling steps along the way. And then to see, with our design process for our new furnace, we have its own material handling aspects to be able to link the whole process together and create that material flow. So hence, yes, the approach for a simulation was very important to us. including, so those steps were the incoming slabs on the rakes, the operation of the yard, each of the 2 yards, the cranes, the transfer car, the slab cutting, the slab assembling, preparing the slabs to be charged into the furnace, the actual charging of the furnace, the heating capacity of the furnace and the rate at which the slabs progress through, and then a complex pacing model to do with rolling, all being linked back to each of their individual downtimes, both planned and also unplanned downtimes. And so with that, we actually, it's not the first time we've engaged in process modeling on this site. We have, for a long time, relied on AnyLogic as our primary use of a process modeling tool. So engaging with a partner who was familiar and capable in that was quite important to us. And so on that, I'll pass you back to Siobhan to keep talking and telling about what we've done.
Thanks a lot, Stephen. And now we'll be delving into the technical modeling bits a little bit. Before that, why AnyLogic was used. Of course, the familiarity with SimWell was one point. Another thing, like even without that, AnyLogic has a lot of flexibility, and the code-based environment in AnyLogic basically gives us more flexibility and kind of modularity when we're modeling things. So basically, we're able to build a great foundation and build on top of that all of the complexities and logic that we need, as well as the ability to combine discrete event and agent-based modeling was also a big thing, where basically the complex crane interactions, as Steven said, where we had to have cranes shadowing each other, as well as prioritizing different tasks and prioritizing which crane will basically move in an area. So for that, we had to combine discrete event as well as agent-based modeling, which AnyLogic is capable to do and is very great at. So that's why we decided that AnyLogic was going to be a better way to model things. Now let's get into the model, where we'll first start with the way scalp or slabs are coming into the model. So here, as you can see in the video that will now play, we have a string of wagons that we call rake, and we have slabs, the blue colored slabs that are coming on those wagons, and the crane in the upper yard is basically working on to kind of take them from the rake and put them in the yard. All of these rakes were based on a schedule, and we had a method to basically prepone the rakes if we had, demand that was earlier, like if we needed the slabs earlier. After this, like the way crane is kind of putting them in the yard is specifically determined, and for that we'll need to understand the stack locations. If we can move to the next slide, Steve. So the stack locations, basically the green, blue, and yellowish rectangles that you're seeing are the stack locations. And these stack locations basically determine which slabs will go where. So slabs we have divided into three main three main three main types. One is which is all based on length, which is 1 unit, 2 unit, 3 unit, and all of these slabs have their unique stack locations that they can go in, and the calculations are so that we are maximizing the space utilized. So basically, a longer slab and a shorter slab go in between each other and all of that. And also, there are a lot of constraints when we are stacking slabs together. So basically, there are overhang constraints, as well as which slabs can go on top of other slabs, as well as we also have to keep in mind we're not burying the slabs that are required earlier by the furnace below those that will be required later, because then we'll have to do unnecessarily, we'll have to unnecessarily dig things out of there. We had to also verify the fact that all of these constraints were kind of followed by the model, and that were done using various metrics that we captured. After this, the upper yard is kind of where all of the rakes come in, and this is where we're unloading the rakes onto the yard. We have one crane modeled in this upper yard, which has two main types of products that it handles. The slab product that we are concerned with in this modeling project, and there's another there's another product that it handles. But we haven't modeled that product in. So that's why we had to be extremely careful about the utilization of this crane in the slab product, so that we can keep in mind that there's also another product that it has to handle. For our project, this crane had three main tasks, which was unloading the rake, as well as loading the transfer car and unloading the transfer car. Transfer car basically acts as a transferring mechanism between the upper yard and lower yard. Lower yard is our primary yard where all of those, all of the operations happen. So basically, we have to move slabs, the bigger slabs from upper yard to lower yard for cutting and charging into the furnace. And also, at times, we have to take stuff from the lower yard into the upper yard, the cut slabs, when they're required later on in the schedule, and we don't want to crowd the space in lower yard. We also made sure that the crane does not collide with other stacks when it's moving about. For that, we had to implement a mechanism where it moves to a safe height first. The lower yard is the primary yard for our modeling purposes, and it can be divided into sub-regions, so to speak, where the whole cutting area can be a sub-region, as well as then there's the assembly area, and then there's the furnace area. So slabs come in from your lower yard, get cut, put into assembly area, and then move on to the furnace area. We have two main cranes that are doing all of this work. The right crane that you see over here is a crane that can pick up multiple slabs at once, and it has tasks. It has a multitude of tasks, basically taking stuff from the transfer car over to the cutter. Then the cutter cuts stuff, and then basically moves it to its kind of output area, from where the crane comes in and puts stuff in the assembly area, and moves it to the furnace charging area. Furnace charging area is what you see on the left side. And the left crane that you see is basically a magnet crane that can only pick up one slab at a once. So for that, basically, we had to model it in such a way that this left crane doesn't have to do any digging. Digging is basically when the slab that you require is underneath some other slabs. So basically, you dig it out, you put the slab somewhere else, and then you dig it out. But we wanted to make sure that everything that reaches this crane is already in sequence. So for that, the crane on the right basically makes sure that whatever it's picking up is already dug out. It basically doesn't only pick one, it picks the next like 4 or 5 slabs that are kind of optimal, and then it places it in the furnace area. And these cranes work in tandem with each other, so we had to make sure that there is no collision and they're shadowing each other properly, where basically one moves out of the way and then other moves in, and then they move together. We made sure to also capture all of the metrics for the crane lift statistics, as well as the yard inventory, all of those things, and the crane utilizations as well for all three cranes. Now let's move on to the slab cutting. So yeah, for the slab cutting, we have, yeah, you can play the video stream. That fits better. We have two main beds where the slab is cut. So it's kind of a simulation inside a simulation. There is a smaller crane that works inside the slab cutter. We haven't modeled that in animation, but it's inside there in the calculations. So that way, basically, it pulls in material from the area on the right and the left where you're seeing the bigger slabs, and then it cuts the slabs, and then all of these slabs are stacked onto the output area, and then they're moved away by the bigger crane that you can see. We had to make sure that all of the slabs are cut in sequence, as well as all of the crane utilization and the number of slabs cut were also made sure to be outputted, so that we can kind of compare them with the real life metrics. Moving on to the next part of the which is kind of the heart of our model, which is the furnace and the rolling mill. We operate furnace in three main modes, which is the single and dual pusher furnace, which is the existing operation, and the newer operation, which is the walking beam furnace, which is what we want to make sure will not like that is kind of the main outcome of our problem, where we want to make sure that everything good there. And then after the furnace, there is the rolling mill, and this rolling mill has sort of 5 steps that it has to take before outputting the slab that has been rolled. These 5 steps have varying, times, and because of this, each slab has varying time for all of these steps. We had to develop a pacing logic that way. The output at the rolling mill is not starved, so we had to make sure that the rolling mill keeps working and the furnace are also full. So we also outputted all of the slab cycle times as well as the throughput out of this rolling mill and furnace to make sure that it's uh, uh, okay with the historical data that we have. Now we'll go on to the operation of these two types of furnace. So here you'll see the single pusher furnace, where you have the roller table on the right, where you see a lot of slabs lined up. A slab comes in, it pushes one of the slabs out. This is, as I said, is maintained by the pacing logic, where basically it determines when a slab would be leaving the furnace. And after the single pusher furnace, where basically a slab comes in and pushes things out, we have the walking beam furnace, which is the new furnace, where basically you have the same slabs lining up, uh, as you can see with the mouse pointer, but now we have 2 slabs ready to be pushed in. So basically you have a discharge step, then you have another discharge, as you can see over here, the red slabs getting discharged. Then you walk the uh, furnace, then you discharge, and then you send 2 slabs in at a time. This is also controlled by the pacing logic, but the difference is that it's much faster because you're putting 2 slabs in, as well as there's the walking step. There's also minimum residence time that we have to meet inside the furnace, which is why you see those colors, where the red slabs have met that minimum residence time and are ready to go into the rolling mill. Uh, Moving on to the next. So this is kind of the logical bits that we thought were interesting. So here you'll see digging. This is kind of an extreme example, but the stack that you saw in green right now is all in reverse order of what we need it to be. So it's 5, 4, 3, 2, 1 instead of 1, 2, 3, 4, 5. And what the crane will do now is basically it will stack them in the reverse order of what it needs. So basically 1, 2, 3, 4, 5. So this is kind of showing the capability of the digging logic that we have developed, where basically generally it will only need to dig out 1 slab, but in this special case, it had to dig out stuff in the reverse order, and it was able to do it pretty nicely. Another interesting bit was related to the crane priorities. So if we can go to the next slide, Steve. Yeah. So we had a data-driven decision table where basically we made sure that the cranes uh, know which task to prioritize, which you'll see in the video now. So look at the right crane in the lower yard. Uh, it will come into view just now. So we have stuff that has come in via the transfer car. So it stops the other task. Because the transfer car has a higher priority to transfer car task. So basically it does that, and then it goes back to the task that it had at hand. And then you'll see that both of the cranes moved in tandem with each other, the left crane as well as the right crane. This was the shadowing bit. So if we can, yeah, let's see the shadowing bit once again, just to make so the transfer car task is picked up, then it starts doing the other task, which had a lower priority. And now they'll move in tandem with each other. Yeah. So the crane shadowing and crane interactions that we had, where the left crane had higher priority. So it basically moved the other crane out of the way. Now, after these were there were other logical bits in the model as well, but these were the main interesting bits that we saw. And now, if we after the modeling, we made sure that model is verified and validated. Verification is basically making sure that what we asked the model is doing what we asked it to do. So it shouldn't be colliding with other cranes. It shouldn't be colliding with other stacks. It shouldn't it should be sending stuff out in the required order. So for all of that, for the cranes, we made sure that we are logging the position of crane as well as the the x-axis position as well as the z-axis position to make sure that it's not colliding with other stacks or other cranes, as well as we outputted all of the cut slabs as well as the slabs coming out of the furnace to make sure that they're all in sequence, they're all working as required. And after that, once we were sure that model was doing what we asked it to do, we made sure that it was validated. So for validation is basically making sure that the model is an adequate representation of real life. So for that, we had the historical data as well as the for the existing operation that we have modeled. What we did was basically we had a lot of output metrics like crane utilization, the mill cycle times, and the throughput of the mill, the slab cutter throughput, and the downtimes. We matched that to the historical data. Crane utilization, we're pretty much good for most of the cranes. One of the cranes, because we had modeled a little conservatively, it was the crane that does a lot of tasks. It was agreed that a 10% gap in between the historical and the actual was good enough. And then the mill cycle times, basically the cycle time of what comes out of, so one slab comes out, then what is the time between the next slab coming out. We also made sure that it was pretty much spot on with the historical data. The slab cutter throughput, we measured it, and basically it was anecdotally verified that it was all good. Asset downtimes, again, pretty much spot on the planned downtimes, and pretty good on the unplanned downtimes. This was all of the technical bits, so to speak. Now I'll hand it over to Stephen to talk through the value that the validation as well as the future state and the outcomes provided to BlueScope Steels and how it helped them.
Yeah, so definitely the verification and validation of the as is or the current state was very, very important. It's what leaders in our business were initially looking for, and to deliver a really close result in basically all areas, and to have a very comprehensive list of metrics was, yeah, it was extremely valuable for our project to build confidence with the rest of the business. The one area where it was I guess not quite as close. We definitely accepted as this is actually the area where we have the most human input, and where people actually come and mess with the normal order of things and do things differently. So it's where we had the most variability from one day to the next. So we were very happy and yeah, to have such close validation. And so as we moved and looked at the future state, that gave us a lot of confidence in being able to give predictions for the business, particularly obviously with a lot of people who are quite concerned about that future state. And we were actually then able to identify from seeing that future state model how we could adapt our approach. And so SimWell were very easy to work with for making some changes to what the future state vision might look like, to do multiple little smaller scenarios, and we were able to identify from starting with a situation of many multiple millions of dollars contingency with some suggestions on what changes we need to make to our project, which are even multiple times what our contingency was, to identify a couple of sub-$1 million sort of opportunities there that we could add to our project that would significantly enhance the overall outcome. And so where we identified that it wasn't all scenarios were under threat or under strain in that material flow process, but it was only quite more significant specific scenarios which we were then able to work with SimWell to come at those solutions. So the overall outcome is basically we were able to deliver confidence to our executive team and the rest of our business that our project was not under threat, would definitely be able to deliver on our business outcomes. We also, it helped us out engaging with our neighbouring departments and clarify within ourselves how the way forward looks. And of course, it helped us save significantly on capital. Yes, we did realize we did have to spend some more capital, but it wasn't, tens of millions of dollars. It was, sub millions. So, yeah, very happy with the outcome. It was a great experience working with SimWell. Thank you, Siobhan. So I'll just note that I'm not seeing any questions in the Q&A. Encourage anyone to put some questions in there now. But yeah, so we are, as we speak, so as we wait for people, so the questions, we are progressing with the project. We have excavated a very large hole in our operating department, which is over 3 meters deep. We have done all of our concrete piling for our foundations. And we are showing that from the work we've done with SimWell that and feedback to the slab yard processes, they've been able to adapt and keep up with our operations. We are currently engaging in sheet piling to then enable us to then dig our deeper basement levels. So we have a question from Dr. Andre. Was the output yard to dispatching also considered, i.e. maybe bottlenecks if more throughput came through? So these yards output into the plate mill and they output into the hot strip mill exclusively. So as Siobhan mentioned, we didn't consider the hot strip mill output directly. We did, however, there is a big interaction in the upper yard between those two plants, and we did consider the increase in inventory and the increased utilization of the assets to make sure that we don't threaten, I guess, the ability for them to supply to the hot strip mill. Like I said, not direct, but definitely indirectly, that was a consideration. We have quite a few questions. Thank you, everyone. Any details on the logic layout in the agents for cranes? Siobhan, throw that to you.
Yeah, that's a kind of a technical question. So in brief, basically, for cranes, if I were to take example for crane, basically inside cranes, it's all agent-based modeling where we look into what the other crane is doing and move this crane accordingly. But the tasks that were coming on were discretely modeled. So basically, they were based on timers as well as other components that we had. So that way, like, I'm not sure if I can give you the whole layout, but it's basically tasks come in, they go into the crane moves according to an agent-based modeling approach, and it also keeps into mind what the other crane is doing. If the other crane is in the way, it asks it to move out of the way depending on the priority and all of that. Then I see, was the slab stacking logic clearly defined in reality by the business, or did you have to make assumptions in the simulation? I'm very thankful for BlueScope, but most of the slab stacking logic was very clearly defined, where we had all of the constraints given by the BlueScope itself, as well as whatever the sequencing of the slabs, the way in which we can sequence the slab was also given by most of the constraints were given by BlueScope. We had to make small assumptions here and there, where basically sometimes it's okay to put slab that would be required later on top of slab that is required now if it's in a certain area, and those assumptions were made. But other than that, all of the things were pretty much defined. We and we had to put in the digging logic, which was kind of something that we made on our own. And it was, how long did it take to develop the simulation? The first phase was 5-ish months, I think. I think the next one is for you, Stephen. How is BlueScope looking to?
Go on. and how it was looking to integrate the simulation results into a dynalytic operation logic for one. So directly, not per se integrating. We have our own warehouse management system in development. We're definitely taking a lot of the learnings from the model. My background is more with the plate mill side, hence why I'm involved with the plate mill upgrade project. But we had another colleague, Darren Evans, who was fantastic to work with. He's the subject matter expert for the slab yard, and he was involved intrinsically throughout this process. Obviously, we couldn't have done that without him, and he's been taking some of these learnings away to integrate into their own existing warehouse management systems that they're actually currently developing and enhancing on at the moment. So did the animations get implemented into any HMI or SCADA? No, short, no, they have not. I guess existing HMIs and SCADA are not directly compatible, I guess, with AnyLogic, and they have their own animations already. A big part of agent is communication. What type of communications do you have? Were they synchronous or asynchronous? Siobhan, were the agents synchronous or asynchronous?
Yeah. So I think if we were to go with traditional definition, they were synchronous agents, where basically real time it will. That is in the simulation itself. We didn't, as I said, we didn't implement that in their actual actual what do you call it, actual yard. But inside the simulation, it was synchronous. I think Amit is already typing an answer. Can you please share a part of tutorial for this model? We'll see if we can whip something up that's sort of like a tutorial then. But yeah, we didn't have any plans right now. But yeah, we'll see if we can whip something up that's sort of like a tutorial. I think Amit has already answered a lot of the questions. Which AnyLogic libraries were used? As Amit said, we just used the process modeling library. The simple crane agent was not it's pretty good, but it wasn't exactly fit for our purpose, where basically we need some prioritization between cranes, as well as prioritization of tasks, as well as the crane shadowing bit, as I mentioned. Did you output a schedule for movement and placement slabs in space and time for a month ahead? There was no scheduling as an output of the simulation. So we didn't, I mean, there was an output of basically what slab is going where at what time, but it wasn't used by BlueScope because the main output was to consider the high level metrics as well as the impact of the walking beam furnace on the inventory space that we have. So for that it was used, but it wasn't used as what would be stacked where sort of schedule.
Mm-hmm. So for everyone who's still with us, out of interest, I should have started sharing this a little earlier, but on the screen now is actually a video capture of the lower yard, as mentioned, and you can see that crane putting the slabs down into the area for slab cutting. This video is actually slightly sped up. The cranes aren't quite this fast. But you can see now that crane is picking up the recently cut slabs to be introduced into the area. Yeah, and I'll let that play in the background to see if there are any more questions. But yeah, so definitely from a BlueScope perspective, it was overall quite successful. And yeah, we're also sharing a lot of the success with other parts of our business. Because I guess we have definitely engaged in process modeling in the past. This is probably one of the largest process modeling exercises we've done. Yeah, lots of opportunities, I think, in other areas of our business to apply a similar approach, particularly as I mentioned, our whole site is approaching 100 years of age, with many of our departments being over 50 years old. And we're very lucky as a business. We've been able to, in recent times, invest quite heavily in modernisation, like as we're doing in the plate mill, and we continue to in other areas.
Yeah, awesome. We have one more question from Sujit. Did you include unplanned breakdown of new furnace and how it bottlenecked the upstream process? Yes, Sujit, we had unplanned as well as planned downtime for the new furnace as well. So the planned downtime was kind of estimated from the historicals that we have and unplanned downtimes as well. And basically, that was also implemented to see what the impact would be on the upstream process. And that basically sorted acted like a relief whenever basically the furnace is on downtime, the other yards could catch up and have extra inventory that could go into the furnace once it comes back online.
Cool. I think we're approaching the end of our time. So I'd like to thank everyone who's come to listen, and I hope it is of great help to everyone. Siobhan, any last words?
Yeah, thanks a lot everyone for attending and basically helping us. It was a great time working with BlueScope and Steven, and we look forward to working with them again and also showing you what we have worked on again. Thanks a lot, everyone. Have a great day.